Hi there, Mr. Sutton bringing you the BC Calculus 7-7 Extra Practice Number 1 solutions on geometric nth term and ratio tests. To test the convergence of this series, we first apply the nth term test. Limit is n approaches infinity of n to the n over n factorial. Now, n factorial is pretty fast growing. The only thing faster is actually the n to the n you see here. This is a top-heavy function, so this is going to go to infinity as n approaches infinity. Since this is not a result of 0, that means this fails the nth term test and diverges. For this problem, we're trying to test the convergence of this series. By the nth term test, 3 to the n grows a bit faster than negative 2 to the n, so this would seem to go to 0 and be inconclusive. But you might notice this is a geometric series. This is essentially negative 2/3 all raised to the nth power. So let me write out the stuff for my geometric series. We've got a geometric series with an r value of negative 2/3. The absolute value of that is just positive 2/3, and that is less than 1. Therefore, by the geometric series test, since this common ratio is less than 1, this is going to converge. For this one, I'm testing convergence for this series. I'm going to start with the nth term test, I always do. To make my life a little bit easier, though, I'm going to rewrite this a little bit. So I could write all of this as 3 to the n over 2 to the n over n cubed. And the 3 and the 2, I can actually move those together into a 3 over 2 to the n exponentiated fraction here. So now that I've rewritten it in this form, taking the limit as n approaches infinity, this is exponential growth with a base that's bigger than 1. So this is going to outgrow any kind of polynomial growth, making this a top-heavy function. This then goes to infinity for the limit, which is not 0. So this is going to diverge then by our nth term test. In trying to find the convergence of this series, I would love to apply the nth term test in the beginning. The only problem is I don't know the nth term of this. I could find it, but it would be faster just to use another test. This, it looks like we keep multiplying by 1.1 each time to get the next number. So this is actually a geometric series with an r value of negative 1.1. So I'm just going to use the geometric series test. I see that the absolute value of the common ratio is 1.1. Since that's greater than or equal to 1, this just fails to converge, diverges by the geometric series test. To test the convergence of this series, I'm going to first apply the nth term test. They did give me the nth term, so let me just take the limit of this as n approaches infinity. So this is essentially the limit of n over n, or just 1. Since this does not equal 0, this diverges by the nth term test. On this problem, I'm trying to figure out if this thing converges or diverges. Let me start with the nth term test. So limit as n approaches infinity of this stuff here. Now, if I take this limit, I notice that I have an exponential term in the numerator versus a polynomial in the denominator. Exponential growth outdoes polynomial growth. So that means that we're going to end up with a top-heavy function that grows to infinity. It's going to be plus or minus infinity because of this negative 1 out in front, but it's still going to be an infinity. It's still going to be not 0, which is the piece that means we fail to converge. We diverge by the nth term test. For this problem, I want to figure out if this series converges. I'll start with the nth term test. If I take the limit as n approaches infinity of all this, I can ignore this 1, and this is really just basically 2/3 to the n power, which is just going to reduce to 0. So that doesn't actually tell me anything useful because nth term test can't prove convergence. So let's keep going. Let's use the ratio test. Let me take the limit as n approaches infinity of absolute value of, and up here I've got the n plus 1th term, 2 to the n plus 1, 3 to the n plus 1, all of that plus 1. Down here I'm going to have the nth term. And now let me simplify the fraction. Same change flip. I've got my numerator of 2 to the n plus 1 times 3 to the n plus 1. And now in the denominator I've got a 2 to the n and this whole 3 to the n plus 1 term. Let me clean this up a little bit. Since I'm taking a limit at infinity, I can ignore these slower growing terms of plus 1s. So I've really just got 2 to the n plus 1 and a 3 to the n in the numerator, and a 2 to the n and a 3 to the n plus 1 in the denominator. Now I can reduce this a little bit. These 2's can reduce to just 2 in the numerator, subtracting those exponents. These 3's can reduce to just 3 in the denominator. So I have a 2 over a 3 when all is said and done for my limit. Since this is less than 1, that means that this series will converge by the ratio test. On this problem, we want to know to what number does this infinite series converge, and does not converge is an option, so we need to take that into account. So let's see if this converges at all. This is a geometric series. We have repeated multiplication of negative e over pi. Since it's geometric, we're going to go ahead and find the a1 and the r values. a1, my first term, is what I get when I plug 0 in for k. That's just all this to the 0, which is just 1. For the r value, that's what I keep multiplying by. That's the negative e over pi in here. And just checking the conversions, the absolute value of that common ratio is just e over pi. And e is smaller than pi. This is like 2.7 and change versus 3.1 and change. So that means this is going to come out to less than 1 overall if I divide those two, which means this will converge by the geometric series test. Okay, let's go ahead and find the sum then. For that I need my infinite sum formula, a1 over 1 minus r. So that's going to be 1 over 1 plus e over pi. And that does not look like any of the answer choices, so let's clean this up a little bit. Let me merge the stuff in the denominator into one big fraction. So this is really pi over pi plus e over pi, which I can turn into e plus pi over pi. And now doing a little same change flip to divide 1 by this fraction, this ends up being pi over pi plus e, which matches answer choice C. For this problem, we're given this geometric series, and we're told the first term is 48 and the third term 12. We want to know what's true about the sum of this infinite series. And we have a few options. They give us specific possible sums, converges but can't determine it, and then diverges. So we definitely have to check to see if this thing even converges or not. To do that, we need to know, since it's a geometric series, we need the common ratio. Common ratio I would normally get by dividing one term by the term right before it, but I don't have two consecutive terms. I have the first term, we skip a term, and then they give me the third term. The key on this one is realizing that to get from the first term to the third term, you have to multiply twice by the common ratio. So we can actually use that to set up an equation and solve for that common ratio. I can write 48 times r squared equals 12. If I multiply twice by the common ratio, I get from the first term to the third term. Solving this for r, we have 12 over 48, which is 1/4. That's going to be r squared. And then square rooting, I have 1/2. And I know it's not going to be plus or minus 1/2 because these numbers, they said that my terms are all positive, greater than 0. So definitely 1/2 is what we're using for r, which is important because we're going to plug r into a formula later on. But before we do that, let's make sure we're converging. For that, I need the absolute value of the common ratio, which is also 1/2. Since that is less than 1, this is going to converge by the geometric series test. So that means that answer choice D is done. We don't want that. It's going to be one of these other choices. Now, we can always find the sum, the infinite sum of a geometric series, if we have an r value of less than 1. And we actually have some information about the first term, which we do. So we can actually eliminate choice C as well. We can definitely find the answer. To do that, we use our infinite sum formula, a1 over 1 minus r. So in this case, that's going to be 48, that's a1, over 1 minus 1/2. Well, this is really just 48 over 1/2. Multiplying by 2, same change flip kind of deal, we end up with 96, which gives us choice B.